All right, class. This is the first of our online lectures. I hope you're taking notes. I think writing stuff down, even if you don't use it again later, it really does sort of force you to pay attention and make some connections in your brain that you don't get just by listening. So I would advise you get a piece of paper out, write down whatever notes you like to take, but do take some notes. So we're going to talk about just what is instrumentation and measurement systems this class about. This is a schematic of a measurement system. So it has something we want to measure, the measure and, which is a word we won't use very often, but that's like if you want to measure temperature, it's the temperature properties. Some sort of a sensor, something that signal conditioning, so measuring the voltage or filters, lots of different ways we want to modify what comes out of the sensor. And then that goes into a recorder or a gauge or something like that. So this is a measurement system with three parts: sensing, signal conditioning, and then recording. It's really important to keep track of the units as we go through this system. For example, if we were measuring temperature, that's what's starting over here. A temperature sensor may change resistance with temperature changes, so it may have units of ohms. We might run that into a signal conditioning that converts it to volts with an amplifier or a voltage divider or something like that. The voltage is going to go into a recorder, and it's probably got enough math built in to convert it to the right units. It might record it in volts, but you might also see the degrees that we'd like for temperature. And so you can think about all of these as having unit conversions, and you really need to know, is it volts, is it millivolts? That makes a big difference, and you can make huge mistakes if you don't keep track of these. All right, so we don't want to be useless. The measurement system must work. And one way we tell if it's working or not is by looking at the error. So error is the measured value that we get from our sensor or our system minus the true value that we have to know some other way. Because it's a subtraction, the sign of the error is meaningful. Negative means that our measurement is too low. So if all your errors are negative, you're measuring too low. Positive error means you're measuring generally too high. It's sign convention is somewhat arbitrary, but it does have meaning. So we'll try to keep track of that. Don't just throw out the sign if you get a negative number. So to quantify the error, to know how much error a system has, we normally calibrate it. And calibration, we have to know what we're measuring ahead of time. So we have to measure something that we know the measurement of already. And we take a lot of measurements and change that value and see how our measurements compared to the answer that we already know. So that's what calibration is. With electronic systems, it's really easy to take thousands of measurements. So we have to use some math to aggregate the information. So we'll have a lot of probability and statistics in this class just to extract as much information as we can if we measure something many, many times. So the kind of information we might want to get is that 95% of a voltage measurement is within plus or minus 1 volt of the true value, the known value. In order to get rid of error, we like to know what its source is. So taking error and dividing it into different categories is a really common approach. And there are many different ways to do this, different categories you can divide things up, and some of them have overlap. It's not that standardized, although some engineering disciplines, if you happen to work in a particular field, everyone may do it the same way. So one kind of statistic is to take the average of a measurement. It really helps to eliminate randomness. So any kind of fluctuations that are evenly distributed can get removed with averaging. If you are always off by the same amount, then averaging doesn't help because you'll just average to that same amount. So if your scale in the bathroom always weighs 10 pounds too heavy, it doesn't matter if you take 100 measurements and average them, you're going to be 10 pounds too heavy on all the measurements. So this is two types of measurements right there. We can divide everything into systematic and random. So if the systematic error is where we get rid of the randomness with an average and then subtract the true value. So this would be like your scale weighing 10 pounds too heavy all the time. And then the random error is the measurement minus the average of the readings. So if you take 100 measurements, you get 100 different random errors, where if you take 100 measurements, you get one systematic error. There's a lot of overlap in the terminology too, and you just have to get used to it. So bias and systematic error are somewhat interchangeable. Precision and random error come up in the same sections. Here's another picture of a way to look at this way of dividing error into systematic and random. We have these measurements that are the x's on the axis here, and if you average them, you get to their centroid. So here's the average measurement, and if this is the true down here on the scale, then we've got a systematic error here, and the random error is different for every single one of these. It's the difference from an individual measurement to the average, but the random error has a maximum that would be this one. Or you could talk about the entire range of random error. So it's just different ways to look at things, and you'll get some homework problems to do this too. All right, so if we look beyond just a single measurement, usually we want to use a measurement system over a range of values. So here is changing what we're measuring on the x-axis and the output of the sensor on the y-axis. So a calibration plot, normally we input known values, so that would go on the x-axis, and we see what the sensor is. So this is a calibration plot arrangement, hopefully linear. That's what we're looking for. And we can put these envelopes here in the dashed lines as uncertainty or error bounds. And we can specify it as a percentage. And we usually just fit a line to the data we get from calibration. So we've talked about random error and precision, P for precision, B for bias, which is related to systematic error. These are, again, the two types. But when we're looking at measuring multiple things, we get a slightly different definition. So the precision, how random is the reading minus the average of the readings, and the bias is the average of the readings. Instead of from the true, usually we subtract it from the curve fit, the straight line that we're using to calibrate with. So we'll see some of these, and again, this isn't the only way to do it. It's really important to not get locked into one way. Your marketing department may want to change how you define errors and things like that too. So sometimes it's good to be a little skeptical when you get numbers from a manufacturer. So just a couple last examples of a calibration kind of data. So here we've changed the temperature, and we measure the voltage, and we curve fit the data. So this blue line is the fit, and that's what we're going to use to change a voltage reading into a temperature reading once we sell our system. And you can see that the actual measurements, these pluses here, have a lot of scatter, so there's a lot of randomness in this one. But if we average them, we get to these red dots, and it actually looks pretty good. It fits the line pretty well. So scatter is reduced by averaging. So this has a large random error, the precision P, but small bias because the curve fit matches pretty well. All right, so this slide is a similar kind of experiment where we're changing the temperature on our temperature system and we're measuring the voltage. And then we fit a straight line to all of our data, and that's what we're going to tell our customer is the calibration curve. So when the customer sensor measures 2 volts, we're going to say it's 28 degrees, kind of a system. This data is very different looking than the previous slide, where these measurements are very tightly grouped. So all the green are together. Averaging does not change very much. The average and the individual measurements are pretty similar. This means that the precision error is very small. It's a very repeatable kind of a system. But because these red dots are far from the curve fit, which is how we have to use our system, the bias is large. So this has got a lot of inaccuracies because it doesn't lie on the straight line. So averaging doesn't really help. It's very tempting to fit some sort of polynomial to all of this data so that it fits and you get a smaller, different kind of bias measurement. That's pretty bad form. Don't do that. The only time you can really do that is if you can justify it with science or with the physics of the system. So for example, some drag sensor might vary with velocity squared, and so then you should fit a quadratic to the system because you know it's got this quadratic form. If you're just fitting stuff to make your experimental data match arbitrarily, then you're kind of cooking the books, and don't do that. So if you don't have anything else, you just need a linear fit, unless you can justify it with some sort of science or physics or engineering analysis. So this system is just inherently less accurate, and we live with that. We tell the truth about it. All right, well, I hope you stayed awake and took some notes. And just to review, some of the things we looked at were the parts of the measurement system, definitions of what error is and different kinds of error, and then looked at the calibration plot, which we take known measurements of known quantities and curve fit them for later use. All right, I will see you in the next lecture, and don't forget to take the little quiz online. You can refer back to these slides if you need to. Bye.